Hello everyone, this is video 12.7. We're going to be looking at approximating areas of irregular shapes. This video and this section is a lot like the shearing section that we looked at a couple sections ago. I don't know if I necessarily call it required or even necessary. I think it's a really good and really important sort of secondary topic. It helps support some ideas. I don't know if I would necessarily call it required or crucial, but it is very helpful. It is very useful. When we get to the end, I'll sort of talk about why this is the case, why I'm saying this and why I feel this way. It's worth the time that we're going to put into it, but it's not going to be a very long discussion. So yeah, just be aware that that's the case. So let's get started. So I'm going to look at this shape three different ways. And so we have this sort of irregular shape here. And we want to know what the area of this shape is. And you can sort of see the difficulty. We've got all the sort of like wavy, curvy parts of this shape. So we would like to know how large the area is, what the area of this shape is. So one way to do this is going to be to over approximate the area. So we're going to over estimate. And we can do this by including all of the boxes where we have the shape. So we'll go over here, over here. So we want to include everywhere that the shape is. And so now we can count this up. This is 3 by 5, so this is 15. This is 2 by 4, that's 8. So we've got 23. So we've got 23 square units. Now, we know that's too large, right? Because we've included a lot of area. I'll now do blue. So we've included a lot of area here that obviously shouldn't be included. So this is our overestimation, 23. Now, even though it's an overestimation, it's really about our lowest overestimation using this sort of method, because at least we didn't include this box, at least we didn't include this box. We didn't include these squares over here that would have made it 24 or 25 if we include both of them. So, using this method strictly, this is as good as we're going to get as our overestimation. Now, let's compare this to our method 2 here, which is our underestimation. So now remember before we had 23 as our over. So I'll make a note here. So now our underestimation is we're only going to include the boxes that are completely filled in. So these are the boxes that we know are completely filled in. And so we count 1, 2, 3, 4, 5, 6, 7. And so our underestimation is going to be 7 square units. So we know that the area is larger than 7 square units, but less than 23 square units. And that's it. I mean, this is, for the most part, what this section is showing us. We can't find the exact area given the tools that we have, right? In this class, there are ways of finding the area, but they're far beyond the scope of this class. So the best that we can hope to do is to give an interval to say, well, it's somewhere between here and here. That's the best we got. Now, we can improve on this method a little bit that we'll look at on the next slide, but we're not really finding the precise area. We're finding this approximation, but this approximation is really, like I said, an interval. We know it's between two values. Now, clearly we can look at this and see this box here is more than half, this box here is more than half, so we know it's at least 8. Absolutely, that's what we're going to look at on the next slide. So if we know that some of these boxes are a little bit more full than others, is there a way that we can sort of improve on that method? And there is. One way that we can do this, I'm going to take green here and I'm going to draw in these extra lines. So rather than use these boxes as 1 unit by 1 unit boxes, I'm going to split them into quarters. And so effectively, I'm going to be working with a smaller box size. I can't talk and draw these lines at the same time. So, and there. Okay. So now I'm going to use the same method that I used before. I'm going to do my overestimation in black, and then I'll do my underestimation in blue. So my overestimation, again, I'm going to include every box that the shape appears in. Now, this one here, I'm going to cheat it a little bit and skip over that. But I'm going to come over here, down here, over, down, and then, yeah, this is in there. So I got to include that. Come down, come over, like that. Over, and then I'll come up here. Yep, it's in there. I gotta come over. I'm gonna decide it's not in there. Come over and then down. Okay. So now I need to count these up. This is 1, 2, 3. This is 1, 2, 3, 4, 5. Well, this is 10 minus 1. This is 9. So this is 18. This is 1, 2. This is 20. This is 2, 4, 6, 8. Yep. This is 7 by 1, 2, 3. So this is 21. So that makes 42. This is 21 and 21 make 42. This is 28. And so this is 70. So I got 70 boxes here, but each box is only a quarter of the unit squared. So really I have 70 1/4 units squared. And so if I divide that out, that's 35 halves, which is 17.5 units squared. So now we can see that we've gone from our overestimation before we were between 7 and 23 using our unit boxes. Now we've dropped that overestimation from 23 down to 17.5. And if I use the blue and go where is completely filled in, yeah, I'm going to kind of cheat that a little bit. Here, over, up, over, that's inside. And then let's come over here. All right. The blue's maybe not as different from the black as I thought it was going to be. All right. So I'll do a double line so I can kind of see it a little bit more clearly. All right. So now I'm going to count up these blues. So I've got 2 here, 2, 4, 6, 7 here, 8 here, 1, 2, 3, 4, 5, 6 here, 1, 2, 3, 4, 1, 2, 3, 4, 5 by 2 makes 10. So that's 20. That's 37. All right. So I've got my underestimation. I've got 37 units squared. But again, each of these squares is a quarter of the unit. So this is 37 fourths. And so that's going to be 9 1/4. 4 goes into 37 9 times with 1 left over, so 9 1/4. So 9 1/4 units. So you can see now we've improved this estimation. I've gone from 23 to 17. So my area I know is less than 17.5, and now is greater than 9 1/4 units squared. I've got to put my units in there. Okay. So A lot like the area of a circle, if we really wanted to sort of find the exact area of this, what I would want to do then is take these boxes and make them as small as possible. So going from 1 unit squared, or by 1 unit, to um, 1/2 by 1/2, or 1/4 by 1/4, as these things start to shrink down, I start to get a better approximation. And then this upper limit and this lower limit, the over approximation and the under approximation, they will eventually collapse on one number, and that number will be our area. That process, though, of making these things infinitesimally small is where we need a lot more sort of difficult, for lack of a better word. I don't want to say sophisticated, but we need more advanced mathematics for that. And this is where we start to get into some topics in calculus. So again, like the area of a circle that we talked about before, there's that extra step that we can go into that we can't go into in this class. But just be aware that something that you're doing in this class is laying the framework for mathematics down the road that the student may see. You still play a part in developing this sense uh, of limit. Really, is what it's called. Is what we're doing. You're still playing a big part in that development. So just be aware of that. This is a nice activity to do with students, and they can see, again, like I said, how this interval gets smaller and smaller and smaller. Um, yeah. All right. So for your checkpoint problem, I want you to find the approximations for the area of this irregular shape. So if you want to do the 1 unit by 1 unit, if you want to break that down into halves, and so then the quarter square units, if you want to break it down even further, I'll leave it up to you how far you want to go into it. But yeah, so find approximations for this area. If you have any questions about anything from this video or anything else in this section, as always, please bring them to class and we'll get them answered. All right, thanks.